Hello, this is Magic 063 Differentiable Manifolds. I'm Dm Kchm, and this video is about smooth maps. We've already seen smooth functions, that's real-valued functions, and the idea here is much the same, but we're working with a general target, M prime, rather than just the reals. So M and M prime are smooth manifolds, dimensions n and n prime, and F is a map from M to M prime. And we start off by assuming that it's continuous. That means for us that if there's an open subset U prime of the target, then its pre-image, F inverse of U prime, is open in the domain. And if you're used to thinking of continuity for metric spaces, or indeed for Rn, then of course there are other definitions, but this is equivalent to sequential continuity and epsilon delta continuity. And this is the formulation that works well for manifolds. It's very convenient when working with open charts, as we'll see in a moment. So take atlases, phi alpha from U alpha to Rn on the domain, and phi prime nu from U prime nu to Rn prime on the target. Take a point, little m. Now I'm not going to take a chart around little m, not yet. I'll take a chart around f of m, so that'll be a chart on the target, that'll be a phi nu prime chart. And clearly little m belongs to the pre-image, F inverse of U prime nu. And at this point I take a chart phi alpha around little m, and I can assume that the domain U alpha is a subset of the pre-image F inverse of U prime nu. So I'm just highlighting where I am. Okay. If that isn't the case, then I just take the intersection of U alpha with F inverse U nu prime. They're two open sets, so their intersection is an open set, and I can restrict phi alpha to that intersection, and it's still a chart, and its domain is now contained within the pre-image of the pre-image F inverse U prime alpha. So now look at this composite here. This has domain phi alpha of U alpha, that's a subset of Rn. Phi alpha inverse takes that back to U alpha. F then takes it across to inside U prime nu, and phi prime nu then takes it into Rn prime. So I now have a map from an open subset of Rn into Rn prime, and I know what smoothness means for maps between open subsets of Rn spaces. And my definition of smoothness for M is going to be that these maps, these local representations of F in coordinate terms, in terms of the chart phi alpha and phi prime nu, all of these maps are smooth. And of course, I need to know that if one of these maps is smooth, and if I then take different charts on the domain and on the target, then the corresponding local representation will be smooth again. And that follows exactly as in the case as for smooth functions. So going through that is a good exercise. I'm sure you can get the general idea pretty quickly. Writing things out carefully takes a little bit more time. So that's the definition. A continuous map, capital F, from M to M prime is smooth if for all points of the domain there are charts, as described above, so that this composite map here, this local representation of F, is smooth between open subsets of Rn spaces. And that's well defined, and it's a natural extension of the concept of a smooth function, which we looked at in an earlier video. I'll go on in a moment to talk more about smooth functions, but just bear in mind that there's the other extreme case of a smooth curve from R into M, and I'll have a lot more to say about those in subsequent videos. Okay, so first of all, a bit of notation. The set of smooth functions on M, this is functions again, notice, the set of smooth functions is denoted by C infinity M. It's an algebra under pointwise operations. By pointwise operations, of course, I just mean the sort of natural thing that if you've got two functions, f and g, then their sum at a point M is simply the sum of the values. That's an M in there, believe it or not. And likewise with multiplication, f times g at M is f of g times g of M. And scalar multiplication is a special case of that. This is a commutative algebra and an associative algebra, and it has a unit element, which is the constant function at 1. And all of the properties of an algebra are very quick to verify. So something that will matter as we go on is that when you have a smooth map from M to M prime, then you get from that a map on the algebras of functions called F upper star. And this is simply defined by taking a function on the target, g, and composing it with f. And this is a map of algebras, and it is an algebra homomorphism. And again, that's very straightforward to check. This is often called, or rather f star of g is often called the pullback of g across f. This is a perfectly good bit of terminology. The only thing to be aware of is that the word pullback has a lot of other uses as well. They're all, in some vague general sense, they're all rather similar, but the details differ. There are pullback vector bundles, there are pullback manifolds, there are pullback connections. A lot of things can be pulled back from a target to a domain, and we'll talk about these later on. So just watch the word, but it is a useful word to use. So that's terminology and some fairly elementary things. So far, bear in mind, the only smooth functions that we have are the constants. And you can't tell much about a manifold by looking at the constant functions on it. In fact, you can't really tell anything at all. So it's crucial to know that a manifold does actually have a decent range of smooth functions. Think about Rn, for example, or indeed simply R. Think of all the enormous range of smooth functions that are defined on the manifold R. And then go up to Rn, and now we're moving to manifolds. So here's a theorem that assures that there are a lot of smooth functions. It goes like this. M's a smooth manifold, and I've written in Hausdorff and Power compact because those are essential conditions to getting this result. And the result is that if you start off with a compact subset K of M, and you take an open subset U, which contains which contains K, then there exists a smooth function on the whole of M such that it's constant at 1 on K, it's constant at 0 outside of M, and in between K and the outside of M, its values lie between 0 and 1. So it sort of plateaus on K. It's level or 0 on the outside of U, the complement of U, and in between the values are limited to between 0 and 1. These are called bump functions, or sometimes test functions. They're important in all manner of theories to do with manifolds. I won't actually give you a reference for this because we'll do a more general result later on. This is not exactly a difficult thing to prove, but it's not entirely easy either. It's a very good idea to look at the case of Rn, which you can find, for example, in Duistermatt and Kolk, and also in the book of Conlon, and that really gives you as good an idea as most people want about the existence of bump functions. Then there's the transition from Rn to a smooth Hausdorff paracompact manifold, and that's another story. We'll talk about things like that later on. Anyway, that clearly gives an enormous number of different smooth functions on any manifold of dimension 1 upwards. And as a result of that, going back up to the top of the slide again, this means that this algebra C infinity M encapsulates a lot about the actual manifold M. And this is a point of view that's been developed a lot in some approaches to manifolds and their generalizations. C infinity M reveals a lot about M, and F upper star reveals a lot about F. And we'll talk quite a bit about F star, F upper star, and F later on. So when you read about an approach to manifolds that's based on, in terms of the functions on the manifold, that's the point of view that's made possible by this result. Okay, now some more things that are a bit more routine and general. First of all, the composition of smooth maps is a smooth map. Easy to believe. I recommend that you sit down and work out the proof, work through the proof. The basic idea is quite simple. Getting all the details right takes a little bit of trouble, but that's a good exercise to have. The identity map is smooth. That's completely straightforward. And therefore smooth maps form a category. More, a smooth map is a diffeomorphism if it's a bijection and its inverse map is also smooth. And again, that's rather like the definition of a diffeomorphism between open subsets of Rn. It's using the same words, bijection with a smooth inverse. And we'll come to questions of characterization later on. And then again, it's straightforward. The composition of two diffeomorphisms is a diffeomorphism. The identity map on a manifold is a diffeomorphism, and the inverse of a diffeomorphism is a diffeomorphism. So those things are all quite straightforward to do. Okay, one last point. There's a piece of terminology, local diffeomorphism, and this is used in two slightly different senses. First of all, it can mean that you've got two manifolds and you've got an open set in each of them, and you've got a diffeomorphism from one open set to the other open set. And that's a perfectly good interpretation of the words local diffeomorphism. And for example, charts, as we've defined them, are local diffeomorphisms in this sense. On the other hand, there's another meaning, which I won't specify yet, we'll come to it fairly soon, concerning maps that are defined on all of the domain and which are close to, but are not actually diffeomorphisms. And although these two uses of the word have a close relationship, they're not exactly the same. And personally, I try to avoid using this terminology, but you'll meet it in books and seminars and on the web, wherever you look. So something to be cautious of. Okay, that's it for the time being.